Okay. Can you all see that?
Yes,
Oh, yeah,
works.
perfect. Well, yeah. So, I mean, thanks for the nice introduction and for, inviting me here in the first place. And also thanks for the very heroic attempt at pronouncing my last name. I know these Dutch phonemes are always a bit tricky. So yeah, today I'm going to talk about uncertainty in machine learning. Right. So we're going to move from the foundations to Bayesian deep learning, which, as was mentioned in the introduction, is what I work about. So like this is maybe the most technical part of the lecture, but we're going to start very gently. So as you've just heard, I'm a computer scientist, right? I'm in the computer science department at TUM. So just to clarify what I'm going to talk about here, right, what this lecture is actually about. So the lecture is going to be about uncertainty in machine learning, right? We're going to talk about probabilities, randomness, different philosophical foundations, how to actually do this in practice, and a bit about Bayesian deep learning. So what it's not explicitly about is, digital twins or life sciences or any of the other things that this course is about, mostly because I'm not very much in that field, right? So like if you've already followed the previous lectures in this course, chances are you probably know much more about digital twins than I do. So I'm going to leave it as an exercise to you, as it were, to figure out how this all fits. But I'm sure there's going to be a lot of overlaps where you can use the techniques we discussed today in the context of digital twins in life sciences or in any other application domain where machine learning is important. Okay, so now that we have that out of the way, quick roadmap for the lecture. I'm going to start with a motivation for why uncertainty is something we should deeply care about in machine learning. Then we're going to start from the very foundations of randomness and probability. I'm going to look a bit into interpretations of probability, Bayesian inference, and then move towards Bayesian deep learning as the final goal. Okay, so why should we care about uncertainty, right? So here's one example that I quite like, and this might even touch on some of the digital twin adjacent stuff. So imagine that you're in a hospital and you want to deploy a diagnostic model, right? So you have a machine learning model that you take a patient and you show the patient data to that model, and the model should tell you whether the patient has a certain disease or not, right? So in this case, it might be a binary classification. Let's say the model decides whether the patient has cancer or not, right? Now, the question is, which of these two models would you use, right? So the first model that I offer you, called model A here, has a high accuracy but no uncertainty. So the overall accuracy is 90%. So across all the patients you might give it, 90% will get the right diagnosis and 10% will get the wrong one. But you don't know which of the 10% are wrong, right? So you don't know which patients will receive the wrong diagnosis. Now, there's another model that you could also alternatively choose, which I call model B here, which has a lower accuracy but has an uncertainty estimation, right? So the overall accuracy across all patients is 75%, but it splits into essentially two halves of patients. So like for half of the patient, we can call them like the easy patients. The model is very highly confident and it's 100% accurate, right? So it's really gonna like perfectly classify those patients. For the other half, the model is very uncertain and it's effectively just random guessing. So it's 50% accuracy, right? So you can see how overall that gives you 75% accuracy, which is lower than 90. But if you think about what you would do as a doctor in a hospital, I hope you might find that model B is actually the much more useful one, right? Because the way you can use it is that you take the 50% of patients for which it's highly confident, there you use the prediction of the model. For the other half of the patients, you just don't use the model and you defer them back to the doctors, right? And now you've actually made the job of the doctors kind of 50% easier, right? They have 50% less workload and can then spend twice as much time on each of the harder patients in the other half. Whereas in the first model case, you will end up diagnosing 10% of the patients wrongly, whatever you do, right? So I think this is often a nice way to illustrate why accuracy is maybe not the only thing you should care about in the real world, but it also makes a difference of how the model is used, right? There's another example that I want to give that is a bit more everyday. So this is about navigating to work or for you maybe to university, right? So imagine you've overslept a bit, you're waking up at 8:30 and now you get to work by 9, right? And we're assuming that you drive or maybe you ride your bike or whatever, but like there's these three different routes through the city, across a highway and through the forest. And so you want to know which route you should take so that you arrive at work in time. Now there's two different AI models that again, like you have some predictive models, they give you some predictions for how long it takes to reach the goal. And now you have two choices. Either you choose tool A or tool B. But what you've read is that tool B is the newer one. And it just had a New York's paper come out, right? So like it's a really flashy, state-of-the-art predictive model. It has the better mean squared error, right? Which is the kind of way we often measure predictive accuracy in regression tasks. So you know that this tool actually is the better model in the conventional machine learning sense. So obviously, like being a smart, informed person, you choose tool B, right? And then you look at the predictions and you say, well, tool B predicts that the city is the fastest route, so I'm going to take the city route. Now you take the city route, you arrive 2 minutes late. Well, okay, that didn't work out, right? Like you wanted to be on time for work and you ended up being late. So what went wrong? Well, let's look at these predictions again and now compare them to the actual ground truth times. So these ones you didn't know before, but like if you had taken these three routes, like these would be the actual times you would have taken. And now what we see is that the highway is in truth the fastest route, right? Which is also correctly predicted by tool A, but not by tool B. But if you compute the accuracy, right, you compute the mean squared error, you can actually do the math, right? Just like subtract the ground truth times from these predictions and square them. You see that tool B actually has the better mean squared error. And that's because it predicts the forest route much better, right? So the forest is the slowest of all the three routes, but it's perfectly predicted by tool B, where it's very much not perfectly predicted by tool A. So tool A is much better at predicting the fast routes and very bad at predicting the slow ones, while tool B is the opposite and ends up having a slightly better accuracy. But again, that leads to the wrong decision, right? Because we don't actually care about correctly predicting the slow routes. We just care about getting the fast route right, because that's the one we want to take, right? Now, let's say we have another tool, C, which now also has uncertainties, right? So far, these two tools, they gave you point estimates. Now, let's say we can estimate our predictive uncertainties, but instead of just getting a single time, we also get a confidence interval. So now that, if you notice, the ranking is the same as in tool B, right? City, highway, forest, like that's the same that ranking that tool B gave you, but now the uncertainties are very different. And so now if you think about it, if you take the city and you're pessimistic about it, if you have plus minus 8 minutes, that could take you up to 33 minutes, right? So it's quite risky because you wouldn't arrive on time. Whereas the highway is much more predictable, like it's a much lower uncertainty. And even if it takes you 2 minutes longer, you're still going to be within the 30 minutes. So you're going to be always on time. And this is another property of this real world decision. Is not only like, do you not care about the slow routes? You don't even care about the fastest route necessarily. What you care about is that you take a route that with high probability gets you there within the 30 minutes you have. Like if it's much faster than 30 minutes, that's nice, but it's not necessary to have a successful outcome. So the takeaway is that in these cases, often the most accurate model is not necessarily the one that gives you the best decision, right? So if you want to make a risk-aware decision, so you want to like safely arrive within the time that you have allocated, you need these uncertainty estimates to make an informed decision. What we saw in both of these examples, like the medical one and this one, is that we had multiple models with different accuracies, but the higher accuracy did not lead to better decisions usually, right? So like the real objective of machine learning, and this is really the point I've been trying to make with these examples, is not just to predict, but to actually support decisions that we make in the real world. And so what we want to do is not minimize necessarily some test error, but to improve the real world outcomes, right? Like the outcome in terms of correct diagnoses of the patients or in terms of getting on to work on time. So especially when the stakes are high, right? Like in the medical case where you really don't want to make any wrong decisions, or when the risks are asymmetric. So that was the getting to work case where like, you have this threshold of 30 minutes, like within which you're happy to arrive and after which you're not. So you have this asymmetry there. Especially in those cases, it's really important to not only think about accuracy, but think about the uncertainty. So prediction quality is not the same as decision quality. And to bridge that gap, it helps to understand uncertainty. So I know that I've essentially like repeated this now a few different times, but I think this is a really important point that also many people in machine learning overlook, right? So if you look at the published papers that people write in these big machine learning conferences, like ICML and NeurIPS, you often have these tables where people just measure predictive accuracy, and then if their model has the best one, they print the numbers in bold and they declare victory, right? And they say we've beat the state of the art, and now we have the best algorithm. But as we saw in many of these applications, that's not actually what matters, right? And so if that's what you take away from this lecture, that's already good, right? So like if you now stop paying attention and play on your phones for the rest of the lecture, I think you've already learned something very important here. And I hope that this is something that also within the machine learning community, we can maybe disseminate this understanding a bit more, that actually like we don't get any points for having, like 97.3% accuracy if the second best model had 97.1. Like what we do get points for is if we can, make better decisions in the real world that lead to better outcomes. And often people forget that that's the ultimate goal of what we should care about. Okay, so now I hopefully convinced you that uncertainty is something that can help, right? So like we should care about uncertainty. We should think about how can we get those uncertainties, right? So in the previous slide, like how do we get these plus minus 2 minutes or 4 minutes kind of estimates? So clearly uncertainty is relatively strongly connected to the concept of randomness, right? And randomness is a tricky concept. So I have a slide here that I adapted from Philip Hennick's course at Tübingen, where he shows these different number sequences and then he asks people which ones are random, right? So like I think in a lecture hall that works quite well. On Zoom, I'm not expecting you to actually react because you're probably half of you are already looking at your TikTok. So I'm just gonna like go through it, but like hopefully you can appreciate what the point is here, right? So if we look at this sequence, you can briefly think for a moment for yourself. Do you think that looks random or not? Right, and then I can tell you where it's from. So this particular sequence was generated by taking a normal six-sided die, rolling it 6 times, and then repeating the ith result I times, right? So you see the first result was a 4, it's repeated once. The second result was a 3, it's repeated twice. The third result is repeated 3 times, 4 times, and so on. So the process of generating this was a random process, right? Like rolling dice. But it would fail a lot of statistical tests of randomness, right? So because of the structure that obviously like it is very regular in the way that the digits kind of are copied. Okay, now we have a second one here. Again, you can look at it. Looks random to you, maybe, right? No way to say. Well, these are actually digits of pi, right? So like, interestingly, it's 2016 to 2025. Maybe that's an interesting range of years that Philip was fond of. But the point is like these are just perfectly deterministic, right? Like you can look up pi or you can compute it for yourself using a computer or a lot of like handiwork and patience, and you're always gonna find these digits in there, right? So like they're perfectly constant numbers that you always get there, whatever you do, right? Next one is a binary string. So now we have a bunch of zeros and ones. Again, you can ask yourself, is it random? There's a lot of ones here. Is that a random thing? I don't know. Now these come from a CD of physically random bits. So back in the day when we didn't have good random number generators, you could actually buy randomness on a CD, right? You could go out into a store and say, I would like some randomness, please. And they would sell you the CD, which in this case used true physical random number generators. So a bit similar to rolling a die, but like probably in some slightly different technological sense. So when these numbers were generated, they were truly random, right? But on the same time, like now they've been on the CD forever. And it's a bit like if you like roll a die and you get a 4, and then you say like, oh, I'm gonna sell random numbers now, and every time someone asks you for a random number, you're gonna hand them that 4, and you say, well, this 4 is perfectly random because I got it from a die. But at the same time, if you keep giving out the same 4, then maybe at some point people can predict that that's what's happening, and then maybe it's not random anymore, right? In his lecture, Philip actually makes the argument that these days people don't really have CD drives anymore, and that also you can't buy the CD anymore. So like there's going to be a point in the history of this world where the last of these CDs will become unreadable. And at that point, the question is, does this sequence turn random again? Because then we can't actually predict it anymore. So you see it's starting to get very muddy here, right? Okay, next sequence, we can move a bit faster. Again, a few numbers. You probably have no idea whether they're random or not. So these were generated by ChatGPT. You just say, give me 10 random digits. So that looks quite random, but if you know the weights of the model and the seed, you can regenerate them with the same prompt, right? Same here, another few random numbers. These were actually like Python random numbers. So these are the ones that you might actually use in practice if you write any code that needs randomness. You're going to call like Python's random library, which uses the so-called Mersenne twister, and we don't have to go into what that means. But it's a clever mathematical tool using prime numbers and stuff that gives you numbers that essentially look random, right? They're not actually random, they're pseudo-random, but they look as if they were random. But if you take the same seed, you also always get the same ones. In this case, the seed was the number that came from ChatGPT. So now if you know that seed, you can always perfectly generate this number again. So it also makes it fully deterministic once the seed is known. Okay, so I hope that wasn't too tedious, right? I think the point of this whole exercise that hopefully was getting across is that it's actually not clear which of these numbers are really random or not, right? Like what that means. And I think that comes from the deeper philosophical understanding that randomness is really in the eye of the beholder, right? So there's no true randomness in general, and even with the dice rolls, right? So we said, oh, the first sequence was generated by rolling dice. Like surely rolling dice is random, right? Like this is what all these games and casinos are about. And this is true if you have no further information, right? Like if you don't know anything and you see someone rolling some dice, it's impossible for you to predict the outcome. But if you knew the precise positions, the masses, the momenta, and the angular momenta of these dice, you can actually perfectly predict the outcome using just Newtonian mechanics, right? So this is this idea of Laplace's demon. Like if you are a kind of omniscient entity that knows about the state of the universe, you can predict the outcome of these dice rolls. So the true sense of randomness is not essentially in the process, and in fact, the whole universe might actually be perfectly deterministic, right? So I'm not a physicist, so don't quote me on this, but in principle, it could be the case that actually everything that happens from one time step to the next is perfectly deterministic. So like true randomness does not actually describe any objective stochasticity in the world, but it's just our degree of inability to predict these outcomes, right? So like if you cannot predict the roll of the dice, then this is a random outcome. If you can predict it, then it's not a random outcome anymore. And as we saw in these like number sequences, sometimes if you don't know the seed of your like Python random number generator, then it is for all purposes random. But if you know the seed, then it's not random, right? Okay, so this I think is an important distinction to understand that if we talk about uncertainty, which as I said connects to randomness, like this is all a very epistemic discussion, right? Like this is not a discussion about how uncertain is the actual world. It's like how uncertain are we about the world given what we know, right? And if we know more, we're less certain. So there's less randomness, there's less uncertainty. If we know less, we are more uncertain and more things seem random to us. Okay. So this is now a very kind of philosophical point. Now to actually make some headway on using these ideas, we have to transform it into math, right? Like we have to start describing this whole randomness, uncertainty type stuff with a language of maths. And the way we do this in modern maths are the Kolmogorov axioms. So like every branch of math has their own axioms, and for probability theory, these are the Kolmogorov axioms. So it's going to be a little bit of math on the side, but it's hopefully not too heavy. So the idea is that we have what we call a sample space. So this is usually denoted by a capital omega. And we call subsets of the sample space events. Right. So now what we want is something that is a probability in mathematical terms, and the probability is defined by three properties. So these are the axioms. The first property is that it's non-negative. So the probability of any event A in this sample space has to be greater or equal to zero. Right? So there's never a negative probability. If it's zero, it's essentially it doesn't happen. If it's greater than zero, it happens at a certain probability, but it can never happen at like negative probability. Okay, so this is very intuitive. Like this is just to, define the space essentially. Then the other end of the spectrum is one, right? So like one is the probability of the entire sample space. And that just means something must happen, right? If we look at all the events in the sample space, right? So like if you roll a die, the whole sample space would be rolling 1, 2, 3, 4, 5, 6. One of these numbers must happen, right? Like there's no case where you roll the die and the die suddenly disappears, right? So like some of the numbers must come out. And this gives us kind of the bounds of probabilities, right? So probabilities are between 0 and 1. 0 is essentially like nothing happens or it doesn't happen. 1 is it always happens. And then the interesting bit in between is maybe the trickiest of the three axioms. This is so-called additivity or sigma additivity, which means that if two events are disjoint, right? So that's how we write this. Like if the kind of the union of these two events is essentially 0, or the empty set, then the probability that either of them happens is just the sum of the two, right? So if we say in the die example again, you can either roll a 1 or a 2, then the probability that you either roll a 1 or a 2 is just the sum of the probabilities for rolling a 1 and the probability for rolling a 2, which in that case would be 1/6 plus 1/6, so 2/6. Right. So this is how probability works now in a very abstract sense. Like if you have all these axioms, you follow all these axioms, then the P that you get out here, that we wrote here always as this letter, will define a probability measure technically on what we call a sigma algebra over the sample space, right? So sample space omega, the sigma algebra we might call A. If you draw this, so I took this nice drawing from my colleague Nikki at CHUM, then essentially you have the experiment. So this happens in the real world, right? And this experiment has outcomes that lie in this space omega. So this is the sample space. And then subsets of these outcomes we map to points in the event space, right? So this the idea of why there's like subsets here and points there is essentially like, let's think about the die again, right? Like the real world die has a lot of physical configurations that all correspond to the outcome we rolled a 6, right? So it might be that I roll the die and it lands a little bit on my left on the table, or it lands a little bit on my right, or maybe it's a bit rotated or not. All of these are different actual outcomes in the universe, but they all are equivalent to the event we care about, which is to roll the 6, right? So this is why sets map to these point events in the sigma algebra. And the probability measure is then defined on the sigma algebra. So it takes a point in here, so like rolling a 6, and it maps it to the 0, 1 interval to assign us a probability for that event. Nice. So this is the basis for what we're talking about. I mean, it sounds a bit abstract, but I hope that in the example, like it became clear what these probabilities are, right? I mean, they essentially, hopefully you should all have a vague enough intuition for probabilities that none of this is surprising to you. It's just that, you know, if you want to do proper serious math, you have to somehow define things so that all your bases are covered. Now I have a funny little quiz question. Which of these two came first? Right. The left one is the casino in Monte Carlo. So this is actually a photo I took last year when I was visiting in Nice for a conference. We took a little train over to Monte Carlo. So this is, you know, a very famous casino. Like obviously Monte Carlo methods are named after it, and we're going to actually see that a bit later in the lecture also, or the Kolmogorov axioms. All right. Now, given that I posed this question, you can probably guess the answer, which is the only one out of the two that would be interesting, namely that the casino is older, right? So the casino was opened in 1865, and the axioms were only published in 1933. And so the point I'm trying to make here is that obviously people were gambling before they had a theory of probability. But the theory of probability really came out of this model of gambling, right? Like the first people that started thinking about probability, they were thinking about games of chance. So it's like it's not a coincidence that often when we introduce probability in the same way that I just did on the previous slides, we talk about rolling dice or something, right? Because like really people had invented dice and they were rolling them and they were betting money and they wanted to understand how much money they would lose or win. So they had to figure out probability to understand that. And this makes it a very young field in maths, right? So, you know, obviously things like geometry, right? The kind of foundations of geometry date back to ancient Greece, to like Euclid and Pythagoras and so on. Whereas, you know, probability is not even 100 years old in that modern sense of the Kolmogorov axioms. So it's a really young field of science. I mean, it's even younger than, quantum mechanics, which often people, say quantum, like this is kind of a modern, cutting edge thing, but quantum stuff was invented in the early 1900s by Max Planck, right? So like the Kolmogorov axioms are even younger than the first papers on quantum mechanics. Okay, so given that they're so young, maybe it's not surprising that people don't really agree on what it means, right? So this is now we have the axioms, we have the math, but to use them in the real world, we have to understand how this math maps onto the world. And so while they give us a formal calculus for probability, we don't really know based on the axioms, what does it mean if I say the probability of event A is 0.7? And there's actually a lot of different schools of thought, but there's two main ones that are going to be relevant for us and that I want to focus on. One is called the frequentist school of thought. So the frequentists believe that what it means to say probability of A is 0.7 is that 0.7 is the long run frequency of A occurring in repeated experiments, right? So if I say the probability of rolling a 6 is 1/6, what that means is if I roll the die infinitely often, the relative frequency of that outcome out of all the outcomes in that series of die rolls is going to converge towards a sixth. Now, the other school of thought is the Bayesian one, which is saying that no, what it actually means is that the degree of belief we should hold in the outcome A is 0.7. So 70% of our belief should be assigned to A given our current knowledge. Right? So this is saying like before you roll the die the first time, you should have 1/6 of your belief saying that the outcome will be a 6. We're going to see in the next few slides how that leads to different approaches to things. So to make it more precise, the frequentists, they look at this limiting frequency over infinite repetitions. Was started by von Mises and then formalized by people like Fisher, Neumann, Pearson. And they really had this view that probabilities should be objective, right? There should be something in the world that is grounded in these repeated experiments. And the only way it's allowed to define a random variable is if you have a repeatable process, like rolling a die. So the key idea is then if you have a hypothesis, right? So you have the hypothesis, for instance, that your die is fair or your coin is fair. If you toss a coin, the hypothesis is the coin is fair. So like each of the outcomes should be the same frequency. Then you can design a hypothesis test where you like throw the coin a certain number of times. And then based on the test, you either reject the hypothesis or you accept it. But so this obviously doesn't work for unique events, right? So like we said, Buffett's only defined for repeatable processes. So like if you ask, what's the probability that my favorite football club will win their next match? A frequentist would say, well, that's not a well-defined question, right? There's no probability for this because this is a one-time event. You cannot repeat that next match infinitely often. Now, the Bayesians would argue that this is a bit useless then, because like we want to answer questions like, what's the probability that my football club will win? Because maybe I want to go and take a bet on it, right? So if I go to the bookmakers and I want to place a bet on my football club winning, I need some way to assign a probability to this. So the Bayesians say, well, probability is just an epistemic thing. It's just a degree of belief. And that obviously harkens back to what we said before about randomness, that randomness might also not be actually a property of the world, but just an epistemic question about what we know, right? So this is named after Thomas Bayes, who was a British Presbyterian minister, but it was really practically developed by Laplace a few decades later, and then axiomatized in just again like less than 100 years ago by people like De Finetti and Savage. So the idea is that probabilities are subjective, right? They reflect our state of knowledge. And if we have hypotheses, instead of testing them in the frequentist sense, we can assign probabilities to these hypotheses and then update them using Bayes' rule. So De Finetti famously said probability does not exist, right? So this is a bit riffing on my previous slide where I said randomness isn't real, right? So like Finetti says probability isn't real. It's just a subjective state of belief that lives in your head, right? Like depending on what you know about the world. But crucially, probabilities can still be rational, they can be coherent, and they can be very useful. So to really like contrast the two views, right? We said long run frequencies versus beliefs under uncertainty. What that means is that frequentists have these very objective probabilities. They believe they should be the same for every person because everyone should be able to repeat those experiments to just like roll the dice or throw the coins and get the same outcomes. In the Bayesian case, they're very subjective. So different people can actually have different probabilities for things, but they have to be coherent in some sense. And we're going to see what that means in a second. When it comes to statistics or machine learning, right, like often we observe data and then we build a model with some parameters. So the frequentist approach is to say, well, the data is random, like the data we observe, we happen to just draw it out of some sampling distribution, but the parameters of our model are fixed, right? Whereas in the case of the Bayesian, it's the opposite. We say, well, the data comes out of the world, right? Like this is fixed and we can't change the data. But the parameters are something we're not sure about. So this is actually random. So we have belief distributions of our parameters. What that means is that the frequentists also don't have priors, right? They do the inference from the data only. So this is why they're objective. Whereas the Bayesians require prior beliefs that you explicitly put into the model. And again, we're going to see this in Bayes' theorem in a few slides. In terms of tools, the frequentists have all kinds of tools, right? P-values, confidence intervals, all kinds of different unbiased estimators and hypothesis tests and weird kind of distributions. The Bayesian only has one tool, which is the posterior. All right. So like once you have the posterior, like this is all there is, right? Like in the Bayesian worldview, the posterior is the answer to all the questions you might have. And then obviously you can derive decisions from the posterior, and depending on what you want to do, you might take the posterior mean, or you might take some kind of other expectation over it, or use it in different ways. But the posterior distribution as a full distribution over your belief state is essentially all that you need to answer any question. And again, as I said, that leads to hypothesis testing on the frequentist side, whereas the Bayesians assign probabilities to hypotheses. Now, you can ask yourself which of these views is more useful, right? In machine learning and engineering and life. And like this is not a rhetorical question. I think it's a valid question, and like sometimes one or the other is more useful. And this is actually like a lot of the historic debate came from the fact that people looked at different problems. So like Fisher, who was a famous frequentist, he looked at this problem of like breeding plants, right? So you might ask the question like, if I pour twice as much fertilizer on my plant, will it grow more fruit? And this is a repeatable experiment. You can do this hundreds of times with different plants and different fertilizers and whatever, and then you can test this hypothesis by looking at the amount of fruit you grow in your fertilizer setting and without. So this is a very frequentist problem. Whereas some famous Bayesians, for instance, like Harold Jeffreys, he studied seismology and earthquakes, right? So he was asking, what's the probability that there will be an earthquake in Europe in the next 10 years, right? Which is a very important question because you'll have to make decisions based on this. You're like, oh, should we invest in earthquake protection or preparedness measures? So you need that probability somehow, but like to a frequentist, that doesn't make sense to say there's a probability for an earthquake because either there's an earthquake or not, but it's not a repeatable experiment. So you see that people study different questions, and that's why they tend to one or the other. Maybe a kind of weak argument that I want to make, and that's the reason why I work a lot on Bayesian methods, is that in machine learning, often I think we tend to have the latter problem, right? So like, as I said in the beginning, we have these questions of, we have a patient coming into the hospital, we want to predict a diagnosis, or we, like want to decide which way to take to work in the morning. Both of these are things that we only do once, right? Like we make this diagnosis for the patient once, and then the patient leaves and gets treated either correctly or incorrectly, right? We take our way to work and then we arrive on time or not, but it's not a repeatable experiment. It's not something we can keep doing all over again, because then the next patient is going to be different and the traffic the next day is also going to be different. So we're not sampling from a repeatable distribution. This is why I think in machine learning, more often than not, we end up in a setting where the Bayesian view is slightly more useful. Okay, so I want to give the frequentists the benefit of arguing for their side, right? So like, why would people be frequentist? Well, objectivity, of course, is something that people like, especially in science. If you tell them like, oh, my scientific beliefs over this question are different from my colleagues because we have different priors, then people somehow find that that's not like proper science. It's hard science. It has to be objective. So this is why they often like to use frequentist methods. It's reproducible, right? Everyone can do the same experiments and should get the same frequencies out. There's a lot of tools that people have used for a while, p-values and confidence intervals that especially scientists know how to use, right? And we can argue a lot about like, is that a good thing for science, right? That you only get your paper published in Nature if the p-value is below 5% or whatever. But it's something that people are used to, and it's being taught in universities. So that's why they use it. And of course, the guarantees you get are something that are useful, right? So like if you get this p-value of 5%, you know that you actually have only a 5% error of like a 5% rate of being wrong. Now, why be a Bayesian? Well, as we said, Bayes rule lets you update your beliefs in light of new data, right? So like Bayes rule has this very sequential understanding that the frequentists don't have, where you can observe some data, then update your beliefs, then observe some more data, update your beliefs again, right? So like it's much easier to add to existing knowledge. So if you have a scientific question and someone does an experiment, and then someone else does a second experiment, you can update your beliefs from the first one, right? And then someone can do a third experiment, and so your beliefs can continuously move towards the evidence. There's also a few cool theoretical results. So like, unfortunately, I don't have time in this lecture to go into it, but like would be a whole another lecture of very cool little results. Just in very brief words, one of them is called coherence. So Cox and Definetti were the two that really pushed that. Let's say like if your beliefs obey certain consistency rules, so that typically means like if you have a certain level of common sense, you cannot be fooled by anyone into making kind of different decisions under the same basis, right? Or like if someone asks you to make bets, you cannot be ripped off by some bets that make you lose money, certainly or stuff. So if you have these kind of beliefs, then they must follow probability theory and they must behave like probabilities. So note that this doesn't say the same, the opposite, right? So like the Bayesian view is to say like what probabilities are is that they are beliefs. This is just saying if you have beliefs and you want these beliefs to make sense, they have to behave like probabilities. So at least one view of probability theory is to say it's a useful tool for updating your beliefs so that you stay consistent. A result that came out of this later by Savage was to say that if you want to make rational decisions, so if you want to maximize expected utility, then you have to do this under some subjective probabilities. So again, you have to follow Bayes' rule and these probabilistic rules. Otherwise, you will not maximize your utility, right? And so this again connects to what I said earlier. Ultimately, we should not care about making the right predictions, but we should care about making the right decisions. And in a very like fundamental decision theoretic sense, the optimal decisions are always the ones that follow Bayesian probabilities. And finally, there's a very technical result, but that is also very interesting due to Wald that says like Bayesian procedures under some, soft assumptions are admissible and minimax optimal, right? So that is a very technical term, but what it means is there's usually no rule, like no procedure for making decisions that is always at least as good or better, all right? So the technical definition is if you had a non-Bayesian rule, non-Bayesian procedure, you can always find another Bayesian procedure that's always at least as good as your non-Bayesian one, and sometimes it's better, right? So you can always do better in a minimax sense by becoming more Bayesian. And finally, it's a universal framework, right? So like all you need is a posterior, as I said, so you can do everything with that. You can do predictive uncertainty, which is what we're going to look at, but you can also use it for data acquisition, for model selection, if you have partial observability, and so on. So like everything you want to do, you can do within that framework. You don't have to come up with new tools. And this is actually something that is very different for frequentism. Like in frequentist methods, every tool you develop is a new paper, right? Like someone has to think about it, like sit down, do some math, and then come up with a new tool, and then they publish it. In the Bayesian setting, it's all the same. It's always like just a posterior. And in fact, there was a famous statistician called Dennis Lindley who tried to derive a very fundamental like framework for frequentist statistics, and he ended up not succeeding. So he tried it for 10 years and he failed, and then he became a Bayesian and he actually wrote a textbook on Bayesian statistics. So that's just a little anecdote. Okay, so to wrap up this discussion, I took this XKCD comic, which I really like, right? So some of you might have seen this. So it's the idea is we have a neutrino detector that can measure whether the sun has just exploded. It's currently the night, so we don't know. So it measures, then it rolls 2 dice, and if they both come up 6, it lies to us, right? Otherwise, it tells the truth. Obviously, the detector rolls the dice. It says, yes, sun has exploded. So the frequentist is like, well, the probability of this happening by chance is 1/36, right? So that's the probability of rolling 2 times the 6. So that's less than 5%. So your p-value is below 5%. So you say, oh, it's statistically significant, the sun has exploded. And the Bayesian, of course, says, I bet you $50 it hasn't, right? Because the Bayesian has a prior, which tells him that probably the sun hasn't exploded because usually it doesn't. And so it's probably still fine. So this is really the core of what I've just been saying. So hopefully that drives the point home that in many cases, the Bayesian reasoning is a bit more commonsensical. Okay, so to look at how we do the Bayesian stuff, as I said, the only thing we need is Bayes' theorem, and so far I haven't showed it to you, but here it is. So the way I wrote it down here is in terms of parameters, usually like this in machine learning, the model parameters, but it could also be some kind of latent variables that we haven't observed. Then there's the observed data D, and we have to define, as I said, our prior. So we have to say, what do we believe about theta, about our parameters before seeing any data? And then there's a likelihood, which is the probability of generating the data given the parameters, right? Like how likely are the data under theta? And this gives us the posterior. So this is our belief after having seen the data. And now there's this nasty term here in the denominator, which is called the evidence. So this is an integral over the numerator of this, right? So we integrate out theta so that this whole thing integrates to 1, because as I said before in the Kolmogorov axioms, probability distribution always has to integrate to 1 because something has to happen with certainty. So this is why we have to solve this integral, and this is gonna be a bit nasty at some point. So we're gonna come back to why that is one of the weaknesses of the Bayesian approach. So if you hear this called the marginal likelihood, like this is the same word, like evidence or marginal likelihood, it's the same. So as a very vague way of remembering this, right, the posterior is essentially proportional to the prior reweighted by the likelihood. Okay, so now let's go into machine learning. So in machine learning, we always like to look at little toy problems. So here I plotted a 1D regression. So this is something that we often like to do because it's easy to look at. So the true function is a sinusoid. And I generated data by sampling from the sinusoid and then adding a bit of noise, right? So like that's why the data points are not exactly on the curve, but they're a bit noisy. And now we can, we imagine we don't know the true function. We just observe the data. We can go and build a model. So the simplest model that machine learning people might build is a linear regression. Right? So this is just drawing a line through here. Now, obviously, the data are not linear, right? Like we know that they weren't generated from a linear function, but as a machine learning person, we might not know this. We just see the data, and we're going to go ahead and fit a linear function. So I'm not going to go into linear regression. I'm assuming that some of you might have seen this before. But now the question is, how can we do this in a Bayesian way? All right, so if we do Bayesian linear regression, the model is the same as a normal linear regression, right? So we say the outputs y are a linear function of x, so x transpose some parameters, theta, that we want to learn. And there's some observation noise, epsilon, which is Gaussian, right? So this is the noise that you saw I added on the measurements. Now the observed data, we call them x and y. We have n of them, right, and data points. And now where it starts to be Bayesian is that we say we put a prior on our parameters theta, right? So we don't just optimize theta like in standard linear regression, but we actually put a prior. And in this case, we put a Gaussian prior. So we say a priori, we don't know whether the function should go up or down, right? So we put a prior that's centered around 0. So that would be a flat line. And then we quantify our uncertainty in that belief with a parameter tau. So tau tells us like how certain are we that the line should be close to 0 versus that it should go up and down. And so now you see we have two different sources of uncertainty, right? We have the uncertainty due to the measurement noise, which is sigma squared, and the uncertainty in our prior belief, which is tau squared, which just happens to be the next letter in the Greek alphabet after sigma. Now the goal is to compute our posterior belief, right? After having seen the data D, how should we update our beliefs over theta from where we are here through this generative processing? Now the way is we write down the likelihood. Now the likelihood is just Gaussian because that's what our generative process was, right? So remember the noise here is Gaussian, so that gives us a nice Gaussian likelihood. Where we say the observations Y should be distributed around a mean of x transposed theta. So this is the linear function with our observation noise. And each data point is independent, right? So like each of the single points we observe, they have their own likelihood because they're not talking to each other. They're not correlated. And so this way we can take a product over all these likelihoods. Now I said the prior is also Gaussian. Now the nice thing is this is Gaussian, this is Gaussian. I told you in Bayes' theorem we have to multiply them together. And so it happens if we multiply Gaussians together, we actually know how that works because Gaussians are very nice. So like if you multiply two Gaussians together, it happens that you get another Gaussian, and we can do that in closed form. So the resulting posterior in this case is what we call conjugate, right? So conjugate means these are both Gaussian, and so the output is also Gaussian. And so it's Gaussian with a mean and a covariance that are given by this, right? So I'm not going to derive this. This is another little homework exercise for you if you want to derive this. It's not very hard. One hint is that if you look at it, you might understand that adding two Gaussians, or like multiplying two Gaussians, means that you add their precision matrices. So the precision matrix of the prior is this thing, and the precision matrix of the likelihood is this one. And then you add them together, and then to get from that added precision back to the covariance, you invert it. And then the mean is essentially the predictive of the function like scaled through this covariance. And if you've ever done ridge regression, right? So like this is going back to the standard frequentist linear regression. If you've done ridge regression, like this is actually the same. So the ridge regression would add a L2 regularizer, right? So this is in the frequentist interpretation, it's not a prior, it's just against overfitting. And they would call this parameter lambda. So like the thing here in front of the identity matrix would be called lambda. And they would say lambda is just our regularization strength, and we can choose that somehow. But this is where the frequentists, they hide the fact from you that this is a prior, right? So like what it really is just the ratio between the variance of your observation noise and your prior beliefs. But in frequentists, they kind of squish this together into one parameter lambda, and they say, yeah, you choose lambda somehow, whatever, it doesn't matter. But the mean is the same, right? So the crucial point is like the mean prediction is the same in both of these models. It's just that the Bayesian one also gives you a covariance that you don't get out of the frequentist one. Right, so now if we have that posterior over parameters, what we ultimately care about, of course, is to make predictions. So you see a new data point, x star, and you want to predict what is y star, what's the output. Then you have to integrate again over this whole thing, right? So you have to integrate out theta out of your posterior and out of the predictive, so the likelihood. And luckily, again, the likelihood is the same, right? This is just, again, this the same likelihood we used before. It's still Gaussian. The posterior is still Gaussian. Everything's Gaussian. So we can again do it in closed form. And again, we get another Gaussian. So the predictive is now just a Gaussian centered around x star transpose mu. And the uncertainty, again, separates into the measurement uncertainty, right, which is from the likelihood, and the uncertainty about the parameters. And these two types of uncertainty, sometimes people might call epistemic and aleatoric, right? So epistemic is the uncertainty over parameters because we don't know the parameters well enough. We haven't seen enough data to be certain. Whereas the aleatoric one is the noise of the observation. So alea is the dice, right? So again, this comes back to dice rolling. But you get like both of them explicitly in this predictive. Now, again, in contrast, the frequentist prediction would only give you a point estimate, right? So you only get the y hat, which is the same one as this mean, right? Because we said theta hat in ridge regression is the same one as mu. So the mean prediction is the same, but you don't get this uncertainty point. Right, so now what look in practice, we can run the same linear regression that I showed you before, but now with a Bayesian view, and now we get this nice uncertainty back, right? So you see, we're not actually certain that this line should be exactly where it is, like it could be anywhere in this range with high probability. Okay. I feel like I have to speed up a little bit, but we're going to get there. So linear regression is fine, right? But clearly these data are not linear. I mean, I showed you before the data are sinusoidal. Like clearly this is underfitting. We need a more flexible model. So how can we get a more flexible model to fit that data? How about polynomials, right? So like linear functions are degree 1 polynomials. Maybe we can try higher orders. So degree 3, for instance, that looks good, right? Like this kind of gives you this nice curvature on the sinusoid. But the problem is a priori, we don't know which degree we should use, right? So how about we use degree 7 or degree 15, right? So 15 is clearly fitting the data itself better, right? It actually goes through a lot of the data points. So it will give you a lower error. But if you look at it, it's also like clearly not the right function that the data came from, right? Like this looks very different from the sinusoid. So this is another problem again in these kind of frequentist settings. It's hard to choose the right degree of polynomial. So typically what you have to do is do this regularization. So again, like in ridge regression, you add a regularization term with a certain lambda that you have to pick. But yeah, so ideally, wouldn't it be nice if there were a model class that could just adjust its complexity to the data, right? Like if the data is simple, it would fit a simple model. If the data are complicated, it fits a complicated one. Now that sounds like a Bayesian problem, right? So specifically, what we have to do is take a prior that assigns a higher probability to the less complex functions, and then only updates to more complex ones if the data likelihood suggests it. So one model class that does that very nicely are so-called Gaussian processes, and we can kind of derive them from the linear regression we just did. So to remind ourselves, in Bayesian linear regression, we place a prior over the weights, that's Gaussian. Now this induces a distribution over the actual functions, right? So if you sample the thetas from this Gaussian, and then you look at the functions that are induced by x transpose theta, what that gives you is another Gaussian distribution over function values that's again zero-centered, but with a variance that's now tau squared, absolute value of x squared, right? And what that suggests, that an idea is instead of placing the prior distribution over the weights theta, maybe we can just skip that part and place the prior directly on the functions. And this is the idea behind Gaussian processes. So Gaussian process is a distribution over functions that essentially behaves like a Gaussian, but in infinite dimensions, right? And so again, like this is a proof I don't have time to do with you, but if you want to look into it, the right search term would be the Kolmogorov extension theorem. So there's the good old Kolmogorov again, the same one with the axioms. So there's this proof that says like if you take a multivariate Gaussian in finite dimensions and you then let the dimensionality go to infinity, it still behaves like a Gaussian, right? Even in infinite dimensions, you can have all the nice properties that Gaussians have. It all kind of works out. And in this particular case, over functions, what that means is that the mean vector of the Gaussian now becomes a mean function that we can put in some x values and it gives us numbers. And the covariance matrix, usually that you could read off covariance entries with like two indices, now becomes a bivariate function that you stick in two numbers or two x values in this case, and it gives you the covariance. Right. And for any finite set of inputs you might stick into this Gaussian process, the vector of function values is a multivariate Gaussian, right? With a mean vector that's just the mean function evaluated at x1 to n, and the covariance matrix is just going to have the entries of the kernel function evaluated at these. And this generalizes Bayesian linear regression in the case that, as we said, if we have a linear regression prior on the weights, that gives us just this linear kernel, right? Where the kernel is just the linear combination of the two inputs weighted by this variance. But we can choose much more interesting kernels. So the linear regression kernel, of course, doesn't give us very interesting functions because it just gives us linear functions. But there are kernels such as the so-called RBF kernel, the radial basis function kernel, that gives us very nice smooth functions that can actually be infinitely smooth, but they can also fit the data if we make them do this right. And so this is a very popular GP prior that's actually also an infinite dimensional basis function, right? So like if we go back to this intuition of polynomials, I told you we can choose degree 7 polynomials, degree 15 polynomials. The RBF kernel is essentially, in some sense, equivalent to a degree infinity polynomial because it has infinitely many basis functions. That's why we also call this a non-parametric method, because it can extend its complexity to any number of data points we have. So any number of data points you fit in there, it can perfectly fit if it wants to. And so if we do the Gaussian process regression on the data I've shown you before, we get this nice smooth curvy function that looks very similar to the sinusoid we put in, but also with some uncertainty around it that comes from the GP posterior. And for some of these tools that I'm going to present in the last few minutes of the lecture, I'm adding little notes up here in the right corner for Python packages you can use them, right? So GPs are one of these tools that I think are underappreciated, that should be used more often, right? For like in classification, it's a bit less clear, but in regression, it's actually very strong baseline methods, right? So if you ever stumble about a regression problem in real life, it's actually not a bad idea to try to use a Gaussian process. And if you want to do this with PyTorch mechanics in the way that it runs on GPU and it uses the PyTorch type of functions, you can use this gPyTorch package. Okay, so now GPs are nice, elegant, non-parametric, calibration uncertainty. This is all good. But what I didn't quite tell you is they scale a little bit badly with data and dimensions, right? So they work, very nicely on these, one-dimensional regression with 20 data points. But if you have a billion data points in a million dimensions, then it'll be harder to get that Gaussian process to work. But we know, obviously, all of us have read the news. Neural networks can do this, right? So like neural networks can work really well in these large high-dimensional data sets, and they scale very nicely with the data and compute we throw at them, and we can learn features and stuff. So ideally, we would like to take the ideas from the Gaussian processes, but move them to neural networks. But the problem is that probabilistic inference is quite challenging, right? So standard deep learning, the way we do it, is about optimization. So that means we want to find the optimal set of parameters for our neural network. And that relies on differentiation. So gradient descent, right? Or stochastic gradient descent. And it turns out that that's very easy. So like we can build all these frameworks like PyTorch, TensorFlow, JAX-on, that automatically differentiate things, right? Autodiff. They automatically differentiate through your whole computational graph and give you all the gradients back. And that is just easy. But in Bayesian learning, we want to marginalize, we want to solve these integrals that I pointed at before. And in the Gaussian process setting, again, everything's Gaussian, so everything's conjugate. So we can solve these integrals in closed form. But in neural networks in general, that's not the case, right? So integrating is hard. So there's this famous quote that says, differentiation is mechanics, integration is art. This is often attributed to Richard Feynman, although I'm not sure that's actually true. I couldn't find a very credible source historically, but it doesn't matter. I think it's a good quote, and it really points at something important here. Okay, so let's say then you're a bit disenchanted with this whole Bayesian idea. You say, oh, okay, like I want to use neural networks, but the Bayesian stuff is too hard. Like, can I do something else? Yes, so I'm going to indulge again in some frequentist stuff because it is useful and it works quite well. So there's one frequentist approach that's called temperature scaling. So the problem is, again, neural networks themselves are quite overconfident. So often the softmax scores you get out don't actually reflect true probabilities. But what you can do is you can take the softmax scores, right? So you take the function outputs of the neural network, which are the logits, and you rescale them with a parameter t. So that's what's called temperature scaling. So this is our temperature parameter. And you can tune that parameter in a way such that these estimated probabilities have a good likelihood. And crucially, you don't do this on the training data, but you do it on a different validation set. Because on the training data, your softmax might overfit, but then on a validation set, it might make some mistakes, and there you can then really tune the calibration. And there's another frequentist approach that's very related, which is called conformal prediction. So it's a similar idea. You kind of construct these sets by tuning some parameter on a validation set such that you actually get these guarantees. And this, like works on finite samples in no distributional assumptions. You don't need a prior. So this is really this frequentist promise of, no priors, very objective probabilities. But it, needs a validation set, right? This is where this repeated experiment idea comes from. You have a training set, but now you have to repeat the experiment of like looking at another data point. So you need an untouched validation set that you have not used to train the model So this is a visualization I took from some paper. It's a neural network trained to classify cats and dogs. Obviously, this input image is neither a cat nor a dog, but the normal trained classifier is very confident that it's a cat. So what we would like is that it tells us I'm not actually sure because it's neither, right? So it should have 50-50 odds. And you can add this calibrator, which in our case is just this 1/t temperature scale, and then tune it on the validation set to make sure that these images that are neither cats or dogs actually get uncertain predictions. Okay, so that was one way of doing it in a frequentist way. Another one is so-called deep ensembles. So in deep ensembles, you train just a set of different neural networks, right? So you repeat the same training. It's a very, very simple process. You just train a neural network, and then you just train another neural network, and then you do that again. Now you have different ones. And so instead of just predicting with one of them, you predict with all of them and average. And the hope is that because there's random seeds and there's like randomness in the stochastic gradients, these networks will find slightly different solutions and make slightly different predictions. So this empirically estimates epistemic uncertainty via the diversity of these models. Now, interestingly, this is related to both frequentist and Bayesian ideas without being exactly the same. So the frequentists have this idea of a bootstrap, where you sample from finite data, you resample from the empirical distribution to mimic sampling variability. This is not exactly what deep ensembles are doing because they usually just train on the same data set, but it's somewhat related to this idea. And in the Bayesian context, we have particle-based approximations, where essentially you move some samples around to look like posterior samples. And you can also do that in a kind of ensemble-like fashion if you add an additional repulsive term to push them apart. But again, that's not usually what people do. So like standard deep ensembles are neither really frequentist nor Bayesian, but they also work quite well. So it's usually worth giving it a shot. Okay, so as I said, like, it's a very simple thing. You don't even probably need this image, but you take an input, you feed it to different neural networks, you take the mean, and that's the output. Okay, well, now that I showed you this frequentist stuff, of course, I want to quickly and in some sense convince you that there's still reasons to be Bayesian about things, right? So ensembles, temperature scaling, they're useful, but they lack some principled foundations, right? And what that means is that they rely on kind of ad hoc approximations, such as, like in the ensembles, just the noise in the initialization of the networks, or in the post-hoc calibration, you need this validation data and stuff. So what's often true in decision-making settings you might have in the real world is that you might want to be able to work with training data alone without having access to validation data. And you might want to update your beliefs sequentially as more data is observed, such as people do in active learning or experimental design. And you might also want to incorporate your prior knowledge, right? If you're a medical expert, maybe you want to put all your medical knowledge that you learned in school and you have whole like bookshelves full of that stuff. You want to put it into your model, right? So for all of these, I think the Bayesian paradigm is still more useful. And so that's the whole idea of Bayesian deep learning. The goal is to approximate these optimal Bayesian decisions. So I told you before, we can prove that under very weak assumptions, the Bayesian decisions are optimal. And we want to approximate them using the flexible representational power of these deep neural networks. So this is what I mostly work on. So for the last few minutes, I'm going to indulge myself in showing you the kind of stuff that we do. So a Bayesian neural network is, as you can probably imagine, a neural network where now the weights are random variables, right? So we do the whole Bayesian stuff on the weights. So we put a prior on the weights, then we observe some data, then we compute the posterior, we get the predictive distribution. Now that's the same as we showed you before. Now the problem is there's two integrals here. There's one integral here and there's one integral here. And both of these are intractable, right? In the Bayesian linear regression or the Gaussian process, these P's were all Gaussian. So like everything here was closed form. But in the neural network case, they're usually not Gaussian. So these things are not closed form. And then it's very hard to compute them. So what we have to do is we have to approximate the posterior. And so usually we say we approximate the posterior over the parameters given D with a distribution that we then call Q, because Q is the next letter after P in the alphabet, so that we call Q of theta. And then the question is, how do we get this Q? And I'm going to show you three different ways of doing this. So the first one is the so-called Laplace approximation, which if you want to play around with it, you can install this torch package so that again works with PyTorch. And the idea is to approximate the posterior with a Gaussian. All right, so how do we get a Gaussian? Well, we use a second order Taylor expansion around the map estimate. So we do normal map estimation using your favorite optimizer, SGD, Adam, Shampoo, what have you. And once you find a map estimate, like as a point estimate, you then look at the curvature around it. So here H is the negative Hessian. So that's the second derivatives. And then you do second order Taylor expansion. So if you're a bit confused why there's no first order term, right? So we have the zeroth order term and the second order term. The first order term that would use the gradient falls away because the gradient is zero at the optimum, right? So our map estimate is by definition, it's an optimum of the loss function. So all the gradients are zero. So that's why the first term falls away. And this is why this whole thing works, right? Like it wouldn't work if there was a first order term. But given that there isn't, we can now take the exponential of all of this. And if you squint a bit, you see like this is something minus something transposed, some kind of Hessian matrix, something minus something. So this is a Gaussian form, right? So if you take an exponential of this, you end up getting a Gaussian. Namely, you get a Gaussian where the mean is now our map estimate, right, theta hat, and the precision matrix is that Hessian. So this is very simple. It's cheap for small networks. Because everything's Gaussian now, you can get the marginal likelihood in closed form, which is pretty nice. The problem is it's obviously only valid near the map, right? We just look at the map and we locally put a Gaussian. So anytime we move away from the map estimate, we can't make any guarantees about anything. So if the loss landscape is complex or has several nodes, that won't capture it, right? And so this is what you see here. So let's see sorry for this slightly pixely graphics. But essentially like the true posterior is the blue curve, right? And then we find the map of the blue curve, which is here. And we put a Gaussian around, which is now the Q distribution, as I said, the green one. As you said, it nicely captures this one part of the posterior, but it obviously misses the entire part here just because it cannot see it, right? Like from the map, like we only see the local curvature. So it's a cheap thing, but it's also, missing out on all. So a slightly more fancy way of doing it is to say, instead of just putting a Gaussian locally, we can actually approximate the posterior with any distribution we want, as long as it's in some family we can search over. So we say with a distribution Q and a family fancy Q. Again, if you want to use this in practice, in PyTorch, like there's a library called Bayesian Torch that does that for you. So to do this, we want to find the Q distribution that has the smallest distance, like divergence and KL divergence to the true posterior over our family. But obviously, we don't know the true posterior, right? If we knew the true posterior, we would already be done. We wouldn't be doing any of this, right? So this optimization problem, unfortunately, we can't directly solve. What we do instead is we maximize the so-called evidence lower bound, which is this term here. So expected log likelihood under the Q distribution minus now the KL of Q with a prior, right? So notice here Q with a posterior, here it's Q with a prior, and the prior we actually know. And so this term we can compute. And I'm going to show you like very briefly why this is the right thing to do. But often the problem is still we need to choose a Q distribution for which this is easy to compute. So either we want to compute the KL, we also want to compute this expectation. So if our Q is too complex and weird, then we cannot compute these things efficiently. So that means in practice, people often still use very simple reparametrizable distributional families, such as mean field Gaussians. So in the end, we're like a little bit back to the problem with Laplace, that people often just choose Gaussians for convenience. So the process is relatively scalable and flexible. You can kind of make a lot of decisions based on like what you know about the problem. It can often underestimate variance. So this is a bit of a property of the KL divergence. It can also miss multiple modes. Again, similar to Laplace, if you choose a Gaussian, you're only going to get one Gaussian. And if there's two modes, you're going to miss the second one. And for more complex families, it's hard to optimize. So you have this trade-off between how complex you want to make the family, which gives you more representational power, but also optimization problems potentially. Okay, we only have a few minutes left. So I'm going to go very fast over this part. So if you can look it up in the slides later. Again, the idea is we have a family of distributions Q. We start with some guess, and then we want to optimize it towards the distribution that's closest in KL divergence to our true posterior. So where does this elbow coming from? I was telling you, right? So if we have the marginal likelihood and an approximate posterior, we can write this marginal likelihood, or like the log marginal likelihood, as a log over the joint, right, between data and parameters. So this is just the standard probability marginalization. And then we can squeeze in our Q, right? So we just add Q over Q, right? So this is just one. But now what we can do is we can use Jensen's inequality, which tells you if you have a log outside of an expectation, you can pull it inside the expectation and you get a lower bound. And then we can, rewrite the joint as the likelihood and the prior. And then if we pull these two terms apart, expectation under Q of log likelihood and expectation under Q of log prior over Q, then we get the KL and we get the expected log likelihood, and this is the elbow, right? So this shows us that the elbow is a lower bound on the marginal likelihood. Now, that still doesn't tell you exactly why you should optimize this, right? So the more interesting way to look at it is to start again with the actual problem, right? So the actual problem was we want to minimize the KL divergence between our proximate distribution Q and our true posterior. So we can just start by writing this down, right? This is how the KL divergence is defined. Expectation under Q of log Q over posterior. Okay, now we use base rule. We can write a posterior as prior times likelihood divided by marginal likelihood, right? So this is just your base rule stuck into here. And now we can again separate terms. So precisely we can take Q over P, which is here. We can just take the likelihood, which again is under the denominator, so it's going to get a minus sign. And we can pull out the marginal likelihood, the evidence, because this doesn't actually depend on theta, right? So the expectation of this is just this thing because it doesn't depend on theta. And now what you see is that this term here is actually the negative elbow. So then we have the KL negative elbow, log marginal likelihood. And if we rearrange, that tells us that the log marginal likelihood is actually the elbow plus this KL term. So the previous slide just told us the elbow is a lower bound. But now this tells us that the gap between this lower bound and the actual marginal likelihood is in fact the KL divergence between approximate and true posterior that we want to minimize. And because the log marginal likelihood is again fixed, right? Like this doesn't depend on theta, like this is a constant. If you want to minimize this part, you want to maximize this other part, right? So like the more you push the elbow upwards, the smaller this gap becomes. And so the smaller gets your KL between the Q and the true posterior. And in fact, if you choose your variational family, Q to be the family of all possible distributions, then the KL will become 0 and your elbow will be exactly the log marginal likelihood. And then optimizing the elbow is essentially another way of doing Bayesian inference, right? Then you get the true base posterior out. Okay, so the last approximation before I'm going to end is Markov chain Monte Carlo. So again, named after the casino that I showed you the photo of. If you want to try this as a Pyro is a software package that does this for you. So here the idea is not to actually fit a distribution directly, but to just draw samples. And the samples should ideally come from the true posterior. And so the way you do is you define a Markov chain whose stationary distribution is the posterior. And there's some classical algorithms like Metropolis-Hastings, Hamiltonian Monte Carlo, but if you do it in neural networks, probably you want to use some stochastic approximations to make it scalable. So things like stochastic gradient Langevin dynamics or stochastic gradient Hamiltonian Monte Carlo. And the update very shortly is essentially just a gradient descent update, right? So this is like your new parameters are the old parameters plus some gradient step plus some noise, right? So epsilon here is Gaussian noise. And the whole trick why this works is because you scale it in the right way, right? So you scale the noise by the square root of the learning rate, or like the square root of twice this learning rate that you have in front of the gradient. And if you do exactly this kind of scaling, then you can prove that this noise is just the right balance to explore the posterior while also still getting, biased towards the higher probability regions. So asymptotically, this is exact, right? If you run this infinitely long, you get exact samples. But obviously, in practice, you cannot run it infinitely long. You can only run it for as much time as you have. So it can get quite expensive the better you want your samples to be, and it doesn't really scale to higher dimensions. There's issues with mixing these chains. So in practice, it's not really what people do a lot just because it's so expensive. But if you really want to get the best samples you can, this is what you should do. And so the way it works is, again, you draw some initial samples from proposal distribution, and then you have these updates where you move around. So these are your gradient step, and sometimes they will step out too far, then you reject them. And if you do this long enough, then just over the whole time dimension of the series, you look at how many samples have I seen at this point, how many at this point, how many here, and so on. And then the distribution you get empirically should follow the true posterior. Right, this is the idea of MCMC. Okay, so we're almost at the end of this time slot, and I want to leave some space for a question or two. So just to quickly wrap up, I hope that I've convinced you that in the real world, making the right decisions under uncertainty matters much more than the predictive accuracy of these methods alone. And if that's what you take away, that's enough for the lecture. If you want to take more away, I hopefully also showed you that Kolmogorov's axioms formalize probability, but that they can be interpreted in these different ways, right? Bayesian versus frequentist, and that randomness in itself is actually not a true, like foundational concept of how the world is, but it's an epistemic question about what we know about the world and what we can predict. If we use Bayesian inference, we can use Bayes' theorem. That gives us a very nice principled framework to update our beliefs and derive optimal decisions under uncertainty, and we just get a posterior, and that's all we need. Gaussian processes are a very nice example of Bayesian regression models. So if you ever want to do regression, especially in lower dimensions, you should try GPs. If you want to do high dimensional stuff, maybe you want to do BNNs. There's a few issues then you have to do with approximate inference. And there's the three different methods, Laplace, variational inference, and MCMC, that you can try to use. And you can go back to the slides to look up the different Python packages. Yeah, so with that, I'll give you another few minutes for questions. Sorry for going a bit long.